Figure 3 shows a diagram of a red blood cell from a turtle and a diagram of a red blood cell from a human. These cells are animal cells. Animal cells do not have, and you go through, all cells have a cytoplasm, all cells have a cell membrane. Only bacteria and plant cells have a cell wall, and only animal and plant cells have a mitochondria, not a bacteria cell or prokaryote. So animal cells do not have a cell wall. The actual length of the red blood cell from a turtle is 20.5 micrometers. Calculate the length of the magnified image of the red blood cell of the turtle when magnified 400 times. So, we know the actual length, we know the magnification. What we don't know is the image length, so the magnified image. That's what we have to work out. So if we look at the formula, if we look at this triangle here, the OMA triangle, observed is above. Normally I wouldn't use triangles, but for biology there's not many equations, and this one's easy to remember, so OMA. Yeah, length is above, that's what we need to find out. So this is a multiplication line, this is a divide line. So by covering this up, we can see that if we multiply magnification by actual length, we will get the observed. So let's move that aside. So 20.5 times 400 will give you 8,200 micrometers. Right, let's move on. The width of the human red blood cell when magnified 400 times is 3.08 millimeters, so that's the image length. Calculate the actual width of the cell and show your answer in standard form. So now we go back to this triangle, and now we're trying to work out the actual width, the A. Before we had the observed, now we have the observed length under the microscope. That's how big it looks through observation. Now we want this. So this is a divide line. Observed divided by magnification will give you the actual length. And because it's in millimeters and the answer is required in millimeters, we don't need to convert units at all. So, firstly, 3.08, which is what it says here, divided by 400, which is what it says here, gives us a actual width of 0.0077 millimeters. But in standard form, what you'd have to do is move this decimal point 1, 2, 3 positions, and because of that, when you write times 10, you have to put a -3 because it indicates that actually this moved forward 3 positions, so we need to move it back to get the real figure. So you have 7.7 times 10 to the -3. Red blood cells are carried in veins and arteries. Figure 4 shows the equipment used to measure the elasticity of an artery. So it's quite a bizarre experiment, this. So we've got a ring of muscular tissue from an artery, we've got a hook, and we've got a mass carrier, and we're basically attaching masses to it and extending the, seeing the elasticity of this artery. Describe a method you could use to see how much the ring of tissue from an artery could stretch before it no longer returned to its original size. So what you'd be doing is basically working out its original length, and then what you do is or just find out where the lower tip was, add a mass and measure the extension, and then take it off and see if it returned back. And then you keep on adding masses and taking them off and seeing if it returns back. When it no longer returns back to its original length, then it's deformed, so it's lost its elasticity, so it's actually stretched, and that's the mass that stretches it, the last one you added that had that effect. So how do we say this? Measure the length of the tissue, add the mass, remove the mass and measure the length of tissue again, repeat with different masses until tissue no longer returns to original length. That's it. Give one safety precaution you need to take when handling animal tissue such as blood vessels. So obviously you do not want to have direct contact with it. If you had a cut, it could be very, very dangerous. So wearing gloves, washing hands, cover wounds, sterilize apparatus after use, anything which basically acts as a barrier or disinfectant is useful here.